that escapes from the star. This matter, still relatively rich in hydrogen, accumulates on the white dwarf, growing steadily denser and hotter. Finally, when the temperature rises to 10 million degrees, the entire star ignites in nuclear fusion. The resulting explosion, similar in concept to a hydrogen bomb but trillions of times more violent, blows the white dwarf completely apart and produces a type Ia supernova. SNIAs have proven particularly useful to astronomers by possessing two separate qualities. First, they produce the most luminous supernova explosions in the cosmos, visible across billions of light-years. Second, nature sets a limit to the maximum mass that any white dwarf can have, equal to about 1.4 times the Sun's mass. Matter can accumulate on a white dwarf's surface only until the white dwarf's mass reaches this limiting value. At that point, nuclear fusion blasts the white dwarf apart, and the blast occurs in objects with the same mass and the same composition, strewn throughout the universe. As a result, all of these white dwarf supernovae attain nearly the same maximum energy output, and they all fade away at almost the same rate after they achieve their maximum brightness. These dual attributes allow SNIAs to provide astronomers with highly luminous, easily recognizable, standard candles, objects known to achieve the same maximum energy output wherever they appear. Of course, the distance to the supernovae affects their brightnesses as we observe them. Two SNIAs, seen in two faraway galaxies, will appear to reach the same maximum brightness only if they have the same distance from us. If one has twice the distance of the other, it will attain only 1/4 of the other's maximum apparent brightness, because the brightness with which any object appears to us diminishes in proportion to the square of its distance. Once astronomers learned how to recognize type Ia supernovae, based on their detailed study of the spectrum of light from each of these objects, they had a golden key with which to unlock the riddle of determining accurate distance. After measuring the distances to the closest of the SNIAs, they could estimate much greater distances to other type Ia supernovae, simply by comparing the brightnesses of the relatively near and distant objects. Throughout the 1990s, two teams of supernova specialists, one centered at Harvard and the other at the University of California at Berkeley, refined this technique by finding how to compensate for the small but real differences among the SNIAs, which the supernovae reveal to us through the details in their spectra. In order to use their newly forged key to unlock the distances to faraway supernovae, the researchers needed a telescope capable of observing distant galaxies with exquisite precision, and they found one in the Hubble Space Telescope. Refurbished in 1993 to correct its primary mirror that had been ground to the wrong shape. The supernova experts used ground-based telescopes to discover dozens of SNIAs in galaxies billions of light-years from the Milky Way. They then arranged for the Hubble telescope, for which they could obtain only a modest fraction of the total observing time, to study these newfound supernovae in detail. As the 1990s drew toward a close, the two teams of supernova observers competed keenly to derive a new and expanded Hubble diagram, the key graph in cosmology that plots galaxies' distances versus the speeds at which the galaxies are moving away from us. Astrophysicists calculate these speeds through their knowledge of the Doppler effect, which changes the colors of the galaxy's light by small amounts that depend on the velocities at which the galaxies. Each galaxy's distance and recession velocity specify a point on the Hubble diagram. For relatively nearby galaxies, these points march upward in lockstep, since a galaxy twice as distant from us as another turns out to be receding twice as fast. The direct proportionality between galaxies' distances and recession velocities finds algebraic expression in Hubble's law, the simple equation that describes the basic behavior of the universe, v equals ho d. Here v stands for recession velocity, d for distance, and ho is a universal constant, called Hubble's constant, that describes the entire universe at any particular time. Alien observers throughout the universe, studying the cosmos 14 billion years after the Big Bang, will find galaxies receding at speeds that follow Hubble's law, and all of them will derive the same value for Hubble's constant, though they will probably give it a different name. This assumption of cosmic democracy underlies all of modern cosmology. We cannot prove that the entire cosmos follows this democratic principle. Perhaps, far beyond the farthest horizon of our vision, the cosmos behaves quite differently from what we see. But cosmologists reject this approach, at least for the observable universe. In that case, V equals ho d represents universal law. With time, however, the value of Hubble's constant can and does change. A new and improved Hubble diagram, one that extended to include galaxies many billions of light-years away, will reveal not only the value of today's Hubble constant Ho, but also the way in which the universe's current rate of expansion differs from its value billions of years ago. The latter value would be revealed by the details of the upper reaches of the graph, whose points describe the most distant galaxies ever observed. Thus, a Hubble diagram extending to distances of many billion light-years would reveal the history of the expansion of the cosmos, embodied in its changing rate of expansion. In striving for this goal, the astrophysics community struck a mother lode of good fortune in having two competing teams of supernova observers. The supernova results, first announced in February 1998, had an impact so great that no single group could have survived the natural skepticism of cosmologists to the overthrow of their widely accepted models of the universe. Because the two observing teams directed their skepticism primarily at each other, they brilliantly searched for errors in the other team's data or interpretation. When they pronounced themselves satisfied, despite their human prejudices, that their competitors were careful and competent, the cosmological world had little choice but to accept, albeit with some restraint, the news from the frontiers of space. What was that news? Just that the most distant SNIAs turned out a bit fainter than expected. This implies that the supernovae are somewhat farther away than they ought to be, which in turn shows that something made the universe expand a bit more rapidly than it should. What provoked this additional expansion? The only culprit that fits the facts is the dark energy that lurks in empty space, the energy whose existence corresponds to a non-zero value for the cosmological constant. By measuring the amount by which distant supernovae turned out to be fainter than expected, the two teams of astronomers measured the shape and fate of the universe. Must engage in a bit of rough and tumble in Greek. A universe with a non-zero cosmological constant requires one additional number to describe the cosmos. To the Hubble constant, which we write as h0 to denote its value at the present time, and to the average density of matter, which alone determines the curvature of space if the cosmological constant is 0, we must now add the density equivalent provided by the dark energy, which, by Einstein's formula E equals mc squared, must possess the equivalent of mass because it has energy. Cosmologists express the densities of matter and dark energy with the symbols omega m and omega lambda, where omega stands for the ratio of the cosmic density to the critical density. Omega m represents the ratio of the average density of all the matter in the universe to the critical density, while omega lambda stands for the ratio of the density equivalent provided by the dark energy to the critical density. Here lambda represents the cosmological constant. In a flat universe, which has zero curvature of space, the sum of omega m and always equals 1, because the total density of actual matter plus the matter equivalent provided by the dark energy exactly equals the critical density. The observations of distant type Ia supernovae measure the difference between omega m and omega lambda. Matter tends to slow the expansion of the universe, as gravity pulls everything toward everything else. The greater the density of matter, the more this pull will slow things down. Dark energy, however, does something quite different. Unlike pieces of matter, whose mutual attraction slows the cosmic expansion, dark energy has a strange property: it tends to make space expand, and thus accelerate the expansion. As space expands, more dark energy comes into existence, so that the expanding universe represents the ultimate free lunch. The new dark energy tends to make the cosmos expand still faster, so the free lunch grows ever larger as time goes on. The value of omega lambda is a measure of the size of the cosmological constant and gives us the magnitude of dark energy's expansionist ways. When astronomers measured the relationship between galaxies' distances and their recession velocities, they found the result of the contest between gravities pulling things together and dark energies pushing them apart. Their measurements implied that omega lambda, omega m equals 0.46, plus or minus about 0.03. Since Astronomers had already determined that omega m equals approximately 0.25. This result sets omega lambda at about 0.71. Then the sum of omega lambda and omega m rises to 0.96, near the total predicted by the inflationary model. Recent new results have sharpened these values and brought this sum even closer to 1. Despite the agreement between the two competing groups of supernova experts, some cosmologists remained cautious. It is not every day that a scientist abandons a long-held belief, such as the conviction that the cosmological constant ought to be zero, and replaces it with a strikingly different one, such as the conclusion that dark energy fills every cubic centimeter of empty space. Almost all the skeptics who had followed the ins and outs of cosmological possibilities finally pronounced themselves convinced after they had digested new observations from a satellite designed and operated to observe the cosmic background radiation with unprecedented accuracy. That satellite, the all-important WMAP described in Chapter 3, began to make useful observations in 2002, and by early 2003 had accumulated sufficient data for cosmologists to make a map of the entire sky, seen in the microwaves that carry most of the cosmic background radiation. Although earlier observations had revealed the basic results to be derived from this map, they had observed only small portions of the sky or shown much less detail. MAP's whole sky map provided the capstone to the mapping effort, and has determined, once and for all, the most important features of the cosmic background radiation. The most striking and significant aspect of this map, as was also true for the balloon-borne observations and for MAP's predecessor, the COBE satellite, lies in its near-featurelessness. No measurable differences in the intensity of the cosmic background radiation arriving from all different directions appear until we reach a precision of about 1 part in 1,000 in our measurements. Even then, the only discernible differences appear as a slightly greater intensity, centered on one particular direction, that matches a corresponding slightly lesser intensity, centered on the opposite direction. These differences arise from our Milky Way galaxy's motion among its neighbor galaxies. The Doppler effect causes us to receive slightly stronger radiation from the direction of this motion, not because the radiation actually is stronger, but because our motion toward the cosmic background radiation slightly increases the energies of the photons that we detect. Once we compensate for the Doppler effect, the cosmic background radiation appears perfectly smooth, until we attain an even higher precision of about 1 part in 100,000. At that level, tiny deviations from total smoothness appear. They track locations from which the CBR arrives with a bit more, or a bit less, intensity. As previously noted, the differences in intensity mark directions in which matter was either a little hotter and denser, or a little cooler and more rarefied, than the average value 380,000 years after the Big Bang. The COBE satellite first saw these differences, balloon-borne instruments and South Pole observations improved our measurements, and then the WMAP satellite provided still better precision in surveying the entire sky. Allowing cosmologists to construct a detailed map of the intensity of the cosmic background radiation, observed with unprecedented angular resolution of about 1 degree. The tiny deviations from smoothness revealed by COBE and WMAP have more than passing interest to cosmologists. First of all, they show the seeds of structure in the universe at the time when the cosmic background radiation ceased to interact with matter. The regions revealed as slightly denser than average at that time had a head start toward further contraction, and have won the competition to acquire the most matter by gravity. Thus the primary result from the new map of the CBR's intensity in different directions is the verification of cosmologists' theories of how the immense differences in density from place to place throughout the cosmos that we see now owe their existence to tiny differences in density that existed a few 100,000 years after the Big Bang. But cosmologists can use their new observations of the cosmic background radiation to discern another, still more basic fact about the cosmos. The details in the map of the CBR's intensity from place to place reveal the curvature of space itself. This amazing result rests on the fact that the curvature of space affects how radiation travels through it. If, for example, space has a positive curvature, then when we observe the cosmic background radiation, we are in much the same situation as an observer at the North Pole who looks along Earth's surface to study radiation produced near the equator. Because the lines of longitude converge toward the pole, the source of radiation seems to span a smaller angle than it would if space were flat. Background radiation. Imagine the time when the radiation finally ceased to interact with matter. At that time, the largest deviations from smoothness that could have existed in the universe had a size that cosmologists can calculate, the age of the universe at that time, multiplied by the speed of light, about 380,000 light-years across. This represents the maximum distance at which particles could have affected one another to produce any irregularities. At greater distances, the news from other particles would not yet have arrived, so they cannot be blamed for any deviations from smoothness. How large an angle would these maximum deviations span on the sky now? That depends on the curvature of space, which we can determine by finding the sum of omega m and omega lambda. The more closely that sum approaches 1, the more closely the space curvature will approach 0, and the larger will be the angular size that we observe for the maximum deviations from smoothness in the CBR. This space curvature depends only on the sum of the two omegas, because both types of density make space curve in the same way. Observations of the cosmic background radiation therefore offer a direct measurement of omega m plus omega lambda, in contrast to the supernova observations, which measure the difference between omega m and omega lambda. The WMAP data show that the largest deviations from smoothness in the CBR span an angle of about 1 degree, which implies that omega m plus omega lambda has a value of 1.02, plus or minus 0.02. Thus, within the limits of experimental accuracy, we may conclude that omega m plus omega lambda equals 1, and that space is flat. The result from observations of distant SNIAs may be stated as omega lambda, omega m equals 0.46. If we combine this result with the conclusion that omega m plus omega lambda equals 1, we find that omega m equals 0.27 and omega lambda equals 0.73, with an uncertainty of a few percent in each number. As already noted, these are the astrophysicists' current best estimates for the values of these two key cosmic parameters, which tell us that matter, both ordinary and dark, provides 27% of the total energy density in the universe, and dark energy 73%. Cosmologists have long known that if the universe has a non-zero cosmological constant, the relative influence of matter and dark energy must change significantly as time passes. On the other hand, a flat universe remains flat forever, from its origin in the Big Bang to the infinite future that awaits us. In a flat universe, the sum of omega m and omega lambda always equals 1, so if one of these changes, the other must also vary in compensation. During the cosmic epochs that followed soon after the Big Bang, the dark energy produced hardly any effect on the universe. So little space existed then, in comparison to the eras that would follow, that omega lambda had a value just a bit above 0, while omega m was only a tiny bit less than 1. In those bygone ages, the universe behaved in much the same way as a cosmos without a cosmological constant. As time passed, however, omega m steadily decreased and omega lambda just as steadily increased, keeping their sum constant at 1. Eventually, hundreds of billions of years from now, omega m will fall almost all the way to 0 and omega lambda will rise nearly to unity. Thus, the history of flat space with a non-zero cosmological constant involves a transition from its early years, when the dark energy barely mattered, through the present period, when omega m and omega lambda have roughly equal values, and on into an infinitely long future, when matter will spread so diffusely through space that omega m must pursue an infinitely long slide toward 0, even as the sum of the two omega s remains equal to 1. Observational deduction of how much mass exists in galaxy clusters now gives omega m a value of about 0.25, while the observations of the CBR and distant supernovae imply a value close to 0.27. Within the limits of experimental accuracy, these two values coincide. If the universe in which we live does have a non-zero cosmological constant, and if that constant is responsible for producing the flat universe that the inflationary model predicts, then the cosmological constant must have a value that makes omega lambda equal to a bit more than 0. 7. 2.5 times the value of omega m. In other words, omega lambda must now do most of the work in making equal to 1. This means that we have already passed through the cosmic era when matter and the cosmological constant contributed the same amount toward maintaining the flatness of space. Within less than a decade, the double-barreled blast from the Type Ia supernovae and the cosmic background radiation has changed the status of dark energy from a far-out idea that Einstein once toyed with to a cosmic fact of life. Unless a host of observations eventually prove to be misinterpreted, inaccurate, or just plain wrong, we must accept the result that the universe will never contract or recycle itself. Instead, the future seems bleak, 100 billion years from now, when most stars will have burnt themselves out, all but the closest galaxies will have vanished across our horizon of visibility. By then, the Milky Way will have coalesced with its nearest neighbors, creating one giant galaxy in the literal middle of nowhere. Our night sky will contain orbiting stars, and nothing else, leaving future astrophysicists a cruel universe. With no galaxies to track the cosmic expansion, they will erroneously conclude, as did Einstein, that we live in a static universe. The cosmological constant and its dark energy will have evolved the universe to a point where they cannot be measured or even dreamt of. Enjoy cosmology while you can. One universe or many? The discovery that we live in an accelerating universe, with an ever-increasing rate of expansion, rocked the world of cosmology early in 1998, with the first announcement of the supernova observations that point to this acceleration. Now that the accelerating universe has received confirmation from detailed observations of the cosmic background radiation, and now that cosmologists have had several years to wrestle with the implications of an accelerating cosmic expansion, two great questions have emerged to bedevil their days and brighten their dreams. What makes the universe accelerate? And why does that acceleration have the particular value that now characterizes the cosmos? The simple answer to the first question assigns all responsibility for the acceleration to the existence of dark energy, or, equivalently, to a non-zero cosmological constant. The amount of acceleration depends directly on the amount of dark energy per cubic centimeter. More energy implies greater acceleration. Thus, if cosmologists could only explain where the dark energy comes from, and why it exists in the amount that they find today, they could claim to have uncovered a fundamental secret of the universe, the explanation for the cosmic free lunch. The energy in empty space that continuously drives the cosmos toward an eternal, ever more rapid expansion and a far future of enormous amounts of space, correspondingly enormous amounts of dark energy, and almost no matter per cubic light year. What makes dark energy? From the deep realms of particle physics, cosmologists can produce an answer. The dark energy arises from events that must occur in empty space, if we trust what we have learned from the quantum theory of matter and energy. All of particle physics rests on this theory, which has been verified so often and so exactly in the submicroscopic realm that almost all physicists accept it as correct. An integral part of quantum theory implies that what we call empty space in fact buzzes with virtual particles, which wink into and out of existence so rapidly that we can never pin them down directly, but can only observe their effects. The continual appearance and disappearance of these virtual particles, called the quantum fluctuations of the vacuum, by those who like a good physics phrase, gives energy to empty space. Furthermore, particle physicists can, without much difficulty, calculate the amount of energy that resides in every cubic centimeter of the vacuum. The straightforward application of quantum theory to what we call a vacuum predicts that quantum fluctuations must create dark energy. When we tell the story from this perspective, the great question about dark energy seems to be, why did cosmologists take so long to recognize that this energy must exist? Unfortunately, the details of the actual situation turn this question into, how did particle physicists go so far wrong? Calculations of the amount of dark energy that lurks in every cubic centimeter produce a value about 120 powers of 10 greater than the value that cosmologists have found from observations of supernovae and the cosmic background radiation. In far-out astronomical situations, calculations that prove correct to within a single factor of 10 are often judged at least temporarily acceptable, but a factor of 10,120 cannot be swept under the rug, even by physics Pollyannas. If real empty space contained dark energy in anything like the amounts proposed by particle physics, the universe would have long since puffed itself into so large a volume that our heads could never have begun to spin. Since a tiny fraction of a second would have sufficed to spread matter out to unimaginable rarefaction. Theory and observation agree that empty space ought to contain dark energy, but they disagree by a trillion to the 10th power about the amount of that energy. No earthly analogy, nor even a cosmic one, can illustrate this discrepancy accurately. The distance to the farthest galaxy that we know exceeds the size of a proton by a factor of 1040. Even this enormous number is only the cube root of the factor by which theory and observation currently diverge concerning the value of the cosmological constant. Particle physicists and cosmologists have long known that quantum theory predicts an unacceptably large value for the dark energy, but in the days when the cosmological constant was thought to be zero, they hoped to discover some explanation that would, in effect, cancel positive with negative terms in the theory and thereby finesse the problem out of existence. A similar cancellation once solved the problem of how much energy virtual particles contribute to the particles that we do observe. Now that the cosmological constant turns out to be non-zero, the hopes of finding such a cancellation seem dimmer. If the cancellation does exist, it must somehow remove almost all of the mammoth theoretical value we have today. For now, lacking any good explanation for the size of the cosmological constant, cosmologists must continue to collaborate with particle physicists as they seek to reconcile theories of how the cosmos generates dark energy with the value observed for the amount of dark energy per cubic centimeter. Some of the finest minds engaged in cosmology and particle physics have directed much of their energy toward explaining this observational value, with no success at all. This provokes fire, and sometimes ire, among theorists, in part because they know that a Nobel Prize, not to mention the immense joy of discovery, awaits those who can explain what nature has done to make space as we find it. But another issue stokes intense controversy as it cries out for explanation. Why does the amount of dark energy, as measured by its mass equivalent, roughly equal the amount of energy provided by all the matter in the universe? We can recast this question in terms of the two omegas that we use to measure the density of matter and the density equivalent of dark energy. Why do omega m and omega lambda roughly equal one another, rather than one being enormously larger than the other? During the first billion years after the Big Bang, omega m was almost precisely equal to 1, while omega lambda was essentially 0. In those years, omega m was first millions, then thousands, and afterward hundreds of times greater than omega lambda. Today, with omega m equals 0.27 and omega lambda equals 0.73, the two values are roughly equal, though omega lambda is already notably larger than omega m. In the far future, more than 50 billion years from now, omega lambda will be first hundreds, then thousands, after that millions, and still later billions of times greater than omega m. Only during the cosmic era from about 3 billion to 50 billion years after the Big Bang do the two quantities match one another even. To the easygoing mind, the interval between 3 billion and 50 billion years embraces quite a long period of time. So what's the problem? From an astronomical viewpoint, this stretch of time amounts to nearly nothing. Astronomers often take a logarithmic approach to time, dividing it into intervals that increase by factors of 10. First the cosmos had some age, then it grew 10 times older, then 10 times older than that, and so on toward infinite time, which requires an infinite number of 10 times jumps. Suppose that we start counting time at the earliest moment after the Big Bang that has any significance. In quantum theory, 10 to 43 seconds after the Big Bang. Since each year contains about 30 million seconds, we need about 60 factors of 10 to pass from 10 to 43 seconds to 3 billion years after the Big Bang. In contrast, we require only a bit more than a single factor of 10 to stroll from 3 billion to 50 billion years, the only period when omega m and omega lambda are roughly equal. After that, an infinite number of 10 times factors opens the way to the infinite future. From this logarithmic perspective, only a vanishingly small probability exists that we should find ourselves living in a cosmic situation for which omega m and omega lambda have even vaguely similar values. Michael Turner, a leading American cosmologist, has termed this conundrum, the question of why we find ourselves alive at a time when omega m and omega lambda are approximately equal, the Nancy Kerrigan problem, in honor of the Olympic figure skater, who asked, after enduring an assault by her rival's boyfriend, "Why me? Why now?" Despite their inability to calculate a cosmological constant whose value comes anywhere close to the measure 1, cosmologists do have an answer to the Kerrigan problem. But they differ sharply on its significance and implications. Some embrace it, some accept it only reluctantly, some dance around it, and some despise it. This explanation links the value of the cosmological constant to the fact that we are here, alive on a planet that orbits an average star in an average galaxy. Because we exist, this argument runs, the parameters that describe the cosmos, and in particular the value of the cosmological constant, must have values that allow us to exist. Consider, for example, what would happen in a universe with a cosmological constant much larger than its actual value. A much greater amount of dark energy would make omega lambda rise far above omega m, not after about 50 billion years but after only a few million years. By this time, in a cosmos dominated by the accelerating effects of dark energy, matter would spread so rapidly apart that no galaxies, stars, or planets could form. If we assume that the stretch of time from the first formation of clumps of matter to the origin and development of life covers at least 1 billion years, we can conclude that our existence limits the cosmological constant to a value between 0 and a few times its actual value, while ruling out of play the infinite range of higher values. This argument gains more traction if we assume, as do many cosmologists, that everything we call the universe belongs to a much larger multiverse, which contains an infinite number of universes, none of which interact with any other, in the multiverse concept. The entire state of affairs embeds in higher dimensions, so space in our universe remains completely inaccessible to any other universe, and vice versa. This lack of even theoretically possible interactions puts the multiverse theory into the category of apparently non-testable, and therefore non-verifiable, hypotheses, at least until wiser minds find ways to test the multiverse model. In the multiverse, new universes are born at completely random times, capable of swelling up by inflation into enormous volumes of space, and of doing so without interfering in the least with the infinite number of other universes. In the multiverse, each new universe springs into existence with its own physical laws and its own set of cosmic parameters, including the rules that determine the size of the cosmological constant. Many of these other universes have cosmological constants enormously larger than ours, and quickly accelerate themselves into situations of near-zero density, no good for life. Only a tiny, perhaps an infinitesimal fraction of all the universes in the multiverse offer conditions that allow life to exist, because only this fraction have parameters that permit matter to organize itself into galaxies, stars, and planets, and for those objects to last for billions of years. Cosmologists call this approach to explaining the value of the cosmological constant the anthropic principle, though the anthropic approach probably offers a better name. This approach toward explaining a crucial question in cosmology has one great appeal: people love it or hate it, but rarely feel neutral about it. Like many intriguing ideas, the anthropic approach can be bent to favor, or at least seem to favor, various theological and teleological mental edifices. Some religious fundamentalists find that the anthropic approach supports their beliefs because it implies a central role for humanity. Without someone to observe it, the cosmos, at least the cosmos that we know, would not, could not, be here, hence a higher power must have made things just right for us. An opponent of this conclusion would note this is not really what the anthropic approach implies. On a theological level, this argument for the existence of God implies surely the most wasteful creator one might imagine, who makes countless universes in order that in a tiny sector of just one of these, life might arise. Why not skip the middleman and follow older creation myths that center on humanity? On the other hand, if you choose to see God in everything, as Spinoza did, you cannot help but admire a multiverse that effloresces universes without end. Like most news from the frontier of science, the concept of a multiverse, and the anthropic approach, can be easily bent in different directions to serve the needs of particular belief systems. As things stand, many cosmologists find the multiverse quite enough to swallow without connecting it to any system of beliefs. Stephen Hawking, who holds the Lucasian Chair in Astronomy at Cambridge University, judges the anthropic approach an excellent resolution of the Kerrigan problem. Steven Weinberg, who won the Nobel Prize for his insights into particle physics, dislikes this approach but pronounces himself in favor, at least for the time being, because no other reasonable solution has appeared. History may eventually show that for now, cosmologists are concentrating on the wrong problem, wrong in the sense that we don't yet understand enough to attack it properly. Weinberg likes the analogy with Johannes Kepler's attempt to explain why the Sun has 6 planets, and why they move in the orbits that they do. 400 years after Kepler, astronomers still know far too little about the origin of planets to explain the precise number and orbits of the Sun's family. We do know that Kepler's hypothesis, which proposed that the spacing of the planet's orbits around the Sun allows one of the 5 perfect solids to fit exactly between each pair of adjoining orbits, has no validity whatsoever, because the solids do not fit particularly well. And because we have no good reason to explain why the planet's orbits should obey such a rule. Later generations may regard today's cosmologists as latter-day Keplers, struggling valiantly to explain what remains inexplicable by today's understanding of the universe. And dangerous, because the anthropic approach smacks of intelligent design arguments. Furthermore, many cosmologists find unacceptable, as grounds for a theory of the universe, the assumption that we live in a multiverse that contains a multitude of universes with which we can never interact, even in theory. The debate over the anthropic principle highlights the skepticism that underlies the scientific approach to understanding the cosmos. A theory that appeals to one scientist, typically the one who thought it up, may seem ridiculous, or just plain wrong, to another. Both know that theories survive and thrive, and other scientists find them best at explaining most of the observational data. The future may not produce a quick resolution to this debate, but it will surely bring forth other attempts to explain what we see in the universe. For example, Paul Steinhardt of Princeton University, who could use some tutoring in creating catchy names, has produced a theoretical, ekpyrotic model of the cosmos in collaboration with Neil Turok of Cambridge University. Motivated by the section of particle physics called string theory, Steinhardt envisions a universe with 11 dimensions, most of which are compactified, more or less rolled up like a sock, so that they occupy only infinitesimal amounts of space. But some of the additional dimensions have real size and significance, except that we can't perceive them because we remain locked into our familiar 4. If you pretend that all of space in our universe fills an infinite thin sheet, you can imagine another, parallel sheet, and then picture the 2 sheets approaching and colliding. The collision produces the Big Bang, and as the sheets rebound from one another, each sheet's history proceeds along familiar lines, giving birth to galaxies and stars. Eventually, the 2 sheets cease to separate and start to approach one another again, producing another collision and another Big Bang in each sheet. The universe thus has a cyclical history, repeating itself, at least in its broadest outlines, at intervals of hundreds of billions of years. Since ekpyrosis means conflagration in Greek, the ekpyrotic universe reminds all those with Greek at the tips of their brains of the great fire that gave birth to the cosmos that we know. This ekpyrotic model of the universe has emotional and intellectual appeal, though not enough to win the hearts and minds of many of Steinhardt's fellow cosmologists. Not yet, anyhow. Something vaguely like the ekpyrotic model, if not this model itself, may someday offer the breakthrough that cosmologists now await in their attempts to explain the dark energy. Even those who favor the anthropic approach would hardly dig in their heels to resist a new theory that could provide a good explanation for the cosmological constant without invoking an infinite number of universes, of which ours happens to be one of the lucky ones. As one of our Crumb's cartoon characters once said, "What a wonderful, wacky world we live in." Wooey. The origin of galaxies and cosmic structure. Discovering galaxies. 2.5 centuries ago, shortly before the English astronomer Sir William Herschel built the world's first seriously large telescope, the known universe consisted of little more than the stars, the sun and moon, the planets, a few moons of Jupiter and Saturn, some fuzzy objects, and the galaxy that forms a milky band across the night sky. Indeed, the word galaxy derives from the Greek galaktos, or milk. The sky also held the fuzzy objects, scientifically named nebulae after the Latin word for clouds, objects of indeterminate shape such as the Crab Nebula in the constellation Taurus, and the Andromeda Nebula, which appears to live among the stars of the constellation Andromeda. Herschel's telescope had a mirror 48 inches across, an unprecedented size for 1789, the year it was built. A complex array of trusses to support and point this telescope made it an ungainly instrument, but when he aimed it at the heavens, Herschel could readily see the countless stars that composed the Milky Way. Using his 48-incher, as well as a smaller, more nimble telescope, Herschel and his sister Caroline compiled the first extensive deep sky catalogue of northern nebulae. Sir John, Herschel's son, continued this family tradition, adding to his father's and aunt's list of northern objects and, during an extended stay at the Cape of Good Hope at the southern tip of Africa, cataloguing some 1,700 fuzzy objects visible from the southern hemisphere. In 1864, Sir John produced a synthesis of the known deep sky objects, a general catalogue of nebulae and clusters of stars, which included more than 5,000 entries. In spite of that large body of data, nobody at the time knew the true identity of the nebulae, their distances from Earth, or the differences among them. Nevertheless, the 1864 catalogue made it possible to classify the nebulae morphologically, that is, according to their shapes. In the we call M as we see M tradition of baseball umpires, astronomers named the spiral-shaped nebulae, spiral nebulae, those with a vaguely elliptical shape, elliptical nebulae. And the various irregularly shaped nebulae, neither spiral nor elliptical, irregular nebulae. Finally, they called the nebulae that looked small and round, like a telescopic image of a planet, planetary nebulae, an act that has permanently confused newcomers to astronomy. For most of its history, astronomy has remained plain-spoken, using descriptive methods of inquiry that greatly resembled those used in botany. Using their lengthening compendia of stars and fuzzy things, astronomers searched for patterns and sorted objects according to them. Quite a sensible step, too. Most people, beginning in childhood, arrange things according to appearance and shape without even being told to do so. But this approach can carry you only so far. The Herschels always assumed, because many of their fuzzy objects span a patch of about the same size on the night sky, that all the nebulae lay at about the same distance from Earth. So to them it was simply good, even-handed science to subject all the nebulae to the same rules of sorting. Trouble is, the assumption that all nebulae lay at similar distances turned out to be badly mistaken. Nature can be elusive, even devious. Some of the nebulae classified by the Herschels are no farther away than the stars, so they are relatively small. Others turned out to be much more distant, so they must be much larger than the fuzzy objects relatively close to us if they are to appear the same size on the sky. The take-home lesson is that at some point you've got to stop fixating on what something looks like and start asking what it is. Fortunately, by the late 19th century, advances in science and technology had empowered astronomers to do just that, to move beyond merely classifying the contents of the universe. That shift led to the birth of astrophysics, the useful application of the laws of physics to astronomical situations. During the same era when Sir John Herschel published his vast catalogue of nebulae, a new scientific instrument, the spectroscope, joined the search for nebulae. The sole job of a spectroscope is to break light into a rainbow of its component colors. Those colors, and features embedded within them, reveal not only fine details about the chemical composition of the light source but also, because of a phenomenon called the Doppler effect, the motion of the light source toward or away from Earth. Spectroscopy revealed something remarkable. The spiral nebulae, which happen to predominate outside the swath of the Milky Way, are nearly all moving away from Earth, and at extremely high speeds. In contrast, all the planetary nebulae, as well as most irregular nebulae, are traveling at relatively low speeds, some toward us and some away from us. Had some catastrophic explosion taken place in the center of the Milky Way, booting out only the spiral nebulae? If so, why weren't any of them falling back? Were we catching the catastrophe at a special time? In spite of advances in photography that brought forth faster emulsions, Enabling astronomers to measure the spectra of ever-dimmer nebulae, the exodus continued and these questions remained unanswered. Most advances in astronomy, as in other sciences, have been driven by the introduction of better technology. As the 1920s opened, another key instrument appeared on the scene, the formidable 100-inch Hooker telescope at the Mount Wilson Observatory near Pasadena, California. In 1923, the American astronomer Edwin P. Hubble used this telescope, the largest in the world at that time, to find a special breed of star, a Cepheid variable star, in the Andromeda Nebula. Variable stars of any type vary in brightness according to well-known patterns, Cepheid variables, named for the prototype of the class, a star in the constellation Cepheus, are all extremely luminous and therefore visible over vast distances. Because their brightness varies in recognizable cycles, patience and persistence will yield an increasing number to the careful observer. Hubble had found a few of these Cepheid variables within the Milky Way and estimated their distances, yet, to his astonishment, the Cepheid he found in Andromeda was much dimmer than any of those. The most likely explanation for this dimness was that the new Cepheid variable, and the Andromeda Nebula in which it lives, sits at a distance much greater than those to the Cepheids in the Milky Way. Hubble realized that this placed the Andromeda Nebula at so great a distance that it could not possibly lie among the stars in the constellation Andromeda, nor anywhere within the Milky Way, and could not have been kicked out, along with all its spiral sisters, during a catastrophe milk spill. Systems of stars in their own right, as huge and as packed with stars as our own Milky Way. In the phrase of the philosopher Immanuel Kant, Hubble had demonstrated that island universes, by the dozens, must lie outside our own star system, for the object in Andromeda merely led the list of well-known spiral nebulae. The Andromeda Nebula was, in fact, the Andromeda Galaxy. By 1936, enough island universes had been identified and photographed through the Hooker and other large telescopes that Hubble, too, decided to try his hand at morphology. His analysis of galaxy types rested upon the untested assumption that variations from one shape to another among galaxies signify evolutionary steps from birth to death. In his 1936 book Realm of the Nebulae, Hubble classified galaxies by placing the different types along a diagram shaped like a musical tuning fork, whose handle represents the elliptical galaxies. With rounded ellipticals at the far end of the handle and flattened ellipticals near the point where the two tines join. Along one tine lie the ordinary spiral galaxies. Those nearest the handle have their spiral arms wound extremely tightly, while those toward the tine's end have increasingly loosely wound spiral arms. Along the other tine are spiral galaxies whose central region displays a straight bar, but are otherwise similar to ordinary spirals. Hubble imagined that galaxies start their lives as round ellipticals and become flatter and flatter as they continue to take shape, ultimately revealing a spiral structure that slowly unfurls with the passage of time. Brilliant. Beautiful. Even elegant. But just plain wrong. Not only were entire classes of irregular galaxies omitted from this scheme, but astrophysicists would later learn that the oldest stars in every galaxy were about the same age, implying that all the galaxies were born during a single era in the history of the universe. For 3 decades, astronomers observed and catalogued galaxies in accordance with Hubble's tuning fork diagram as ellipticals, spirals, and barred spirals, with irregulars a minority subset. Completely off the chart because of their strange shapes. Of elliptical galaxies one might say, as Ronald Reagan did about California's redwoods, that when you've seen one, you've seen them all. Elliptical galaxies resemble one another in possessing neither the spiral arm patterns that characterize spirals and barred spirals, nor the giant clouds of interstellar gas and dust that give birth to new stars. In these galaxies, star formation ended many billion years ago, leaving behind spherical or ellipsoidal groups of stars. The largest elliptical galaxies, like the largest spirals, each contain many 100 billion stars, perhaps even 1 trillion or more, and have diameters close to 100,000 light-years. With the exception of professional astronomers, no one has ever sighed over the fantastic patterns and complex star formation histories of an elliptical galaxy for the excellent reason that, at least in comparison with spirals, ellipticals have simple shapes and straightforward star formation. They all turned gas and dust into stars until they could do so no more. Happily, spirals and barred spirals furnish the visual excitement so lacking in ellipticals. The most deeply resonant of all the galaxy images that we may ever see, a view of the entire Milky Way taken from outside it, will stir our hearts and minds, just as soon as we manage to send a camera several 100,000 light-years above or below the central plane of our galaxy. Today, when our most far-flung space probes have traveled a billionth of that distance, this goal may seem unattainable, and indeed even a probe that could reach nearly the speed of light would require a long wait, far longer than the current span of recorded history, to yield the desired result. For the time being, astronomers must continue to map the Milky Way from inside, sketching the galactic forest by delineating its stellar and nebular trees. These efforts reveal that our galaxy closely resembles our closest large neighbor, the Great Spiral Galaxy in Andromeda, conveniently located about 2.4 million light-years away. The Andromeda Galaxy has provided a wealth of information about the basic structural patterns of spiral galaxies, as well as about different types of stars and their evolution. Because all of the Andromeda Galaxy's stars have the same distance from us, astronomers know that the stars' brightnesses correlate directly with their luminosities, that is, with the amounts of energy they emit each second. This fact, denied to astronomers when they study objects in the Milky Way but applicable to every galaxy beyond our own, has allowed them to draw key conclusions about stellar evolution with greater ease than would be true for stars in the Milky Way. Two elliptical satellite galaxies that orbit the Andromeda Galaxy, each containing a few % of the number of stars in the main galaxy, have likewise furnished important information about the lives of stars, and the overall galactic structure of elliptical galaxies. On a clear night far from city lights, a keen-eyed observer who knows where to look can spot the fuzzy outline of the Andromeda Galaxy, the most distant object visible to the unaided eye, shining with light that left on its journey while our ancestors roamed the gorges of Africa in search of roots and berries. Like the Milky Way, the Andromeda Galaxy lies midway along one tine of Hubble's tuning fork diagram, because its spiral arms are neither particularly tightly nor loosely wound. If galaxies were animals in a zoo, there would be one cage devoted to ellipticals but several animal houses for the glorious spirals. To study a Hubble telescope image of one of these beasts, typically seen from 10 or 20 million light-years, is to enter a world of sight so rich in possibility, so deep in separation from life on Earth, so complex in structure, that the unprepared mind may reel, or may provide a defense by reminding its owner that none of this can thin the thighs or heal the fractured bone. Irregulars, the orphans of the galactic class system, comprise about 10% of all galaxies, with the rest split between spirals and ellipticals, strongly favoring spirals. In contrast to ellipticals, irregular galaxies typically contain a higher proportion of gas and dust than spirals do, and offer the liveliest sites of ongoing star formation. The Milky Way has two large satellite galaxies, both irregular, confusingly named the Magellanic Clouds because the first white men to notice them, sailors on Magellan's circumnavigation of Earth in 1520, thought at first they were seeing wisps of clouds in the sky. This honor fell to Magellan's expedition because the Magellanic Clouds lie so close to the south celestial pole that they never rise above the horizon for observers in the most populated northern latitudes, including those in Europe and most of the United States. Each of the Magellanic Clouds contains many billion stars, though not the hundreds of billions that characterize the Milky Way and other large galaxies, and display immense star-forming regions, most notably the Tarantula Nebula of the Large Magellanic Cloud. This galaxy also has the honor of having revealed the closest and brightest supernova to appear during the past 3 centuries, supernova 1987A, which must have actually exploded about 160,000 BC for its light to reach Earth in 1987. Elliptical, or irregular. They had right on their side, since more than 99% of all galaxies fit one of these classes. But during that fine decade, an American astronomer named Halton Arp became the champion of galaxies that did not fit the simple classification scheme of the Hubble tuning fork diagram plus irregulars. In the spirit of, give me your tired, your poor, your huddled masses, Arp used the world's largest telescope, the 200-inch Hale telescope at the Palomar Observatory near San Diego, California, to photograph 338 extremely disturbed-looking systems. ARP's Atlas of Peculiar Galaxies, published in 1966, became a veritable treasure chest of research opportunities on what can go bad in the universe. Although peculiar galaxies, defined as galaxies with such strange shapes that even irregular fails to do them justice, form only a tiny minority of all galaxies, they carry important information about what can happen to galaxies gone wrong. It turns out, for example, that many embarrassingly peculiar galaxies in ARP's atlas are the merged remnants of two once-separate galaxies that have collided. This means that those peculiar galaxies are not different kinds of galaxies at all, any more than a wrecked Lexus is a new kind of car. To track how such a collision unfolds, you need a lot more than pencil and paper, because every star in both galactic systems has its own gravity, which simultaneously affects all the other stars in the two systems. What you need, in short, is a computer. Galaxy collisions are stately dramas, taking hundreds of millions of years from beginning to end. Using a computer simulation, you can start and pause as you like a collision of two galaxies, taking snapshots after 10 million years, 50 million years, 100 million years. At each time things look different. And when you step into ARP's atlas, bada bing, here's an early stage of a collision, and there's a late stage. Here's a glancing blow, and there's a head-on collision. Although the first computer simulations were done in the early 1960s, it wasn't until 1972 that Aller and Yuri Tumor, brothers who both teach at MIT, generated the first compelling portrait of a deliberately simple-minded collision between two spiral galaxies. The Tumor's model revealed that tidal forces, differences in gravity from place to place, actually ripped the galaxies apart. As one galaxy nears the other, the gravitational force rapidly grows stronger at the leading edges of the collision, stretching and warping both galaxies as they pass by or through each other. That stretching and warping accounts for most of what's peculiar in ARP's Atlas of Peculiar Galaxies. How else can computer simulations help us to understand galaxies? Hubble's tuning fork distinguishes normal, spiral galaxies from spirals that show a dense bar of stars across their centers. Simulations show that this bar could be a transitory feature, not the distinguishing mark of a different galactic species. Contemporary observers of barred spirals might simply be catching such galaxies during a phase that will disappear in 100 million years or so. But since we can't hang around long enough to watch the bar disappear in real life, we have to watch it come and go on a computer, where a billion years can unfold in a matter of minutes. Outlines astronomers began to discern during the 1960s and came to understand a few decades later. Before we can appreciate this emergent galactic zoo, we must resume the story of cosmic evolution where we left it. We must examine the origin of all galaxies, normal, nearly normal, irregular, peculiar, and knock your socks off exotic, to see how they were born, and how the luck of the draw has left us in our relatively calm location in space, adrift in the suburbs of a giant spiral galaxy, some 30,000 light-years from its center and 20,000s of light-years from its diffuse outer edge. Thanks to the general order of things in a spiral galaxy, first imposed on the gas clouds that later gave birth to stars, our Sun moves in a nearly circular orbit around the center of the Milky Way, taking 240 million years for each trip. Today, 20 orbits after its birth, the Sun should be good for another 20 or so before calling it quits. Meanwhile, let's have a look at where galaxies came from. The origin of structure. When we examine the history of matter in the universe, looking back through 14 billion years of time as best we can, we quickly encounter a single trend that cries out for explanation. Throughout the cosmos, matter has consistently organized itself into structures. From its nearly perfectly smooth distribution soon after the Big Bang, matter has clumped itself together on all size scales, to produce giant clusters and superclusters of galaxies, as well as the individual galaxies within those clusters, the stars that congregate by the billions in every galaxy. And quite possibly much smaller objects, planets, their satellites, asteroids, and comets, that orbit many if not most of those stars. To understand the origin of the objects that now compose the visible universe, we must focus on the mechanisms that turned the universe's formerly diffuse matter into highly structured components. A complete description of how structures emerged in the cosmos requires that we meld two aspects of reality whose combination now eludes us. As seen in earlier chapters, we must perceive how quantum mechanics, which describes the behavior of molecules, atoms, and the particles that form them, fits with general relativity theory, which describes how extremely large amounts of matter and space affect one another. Attempts to create a single theory that would unite our knowledge of the subatomically small and the astronomically large began with Albert Einstein. They have continued, with relatively little success, right up to the present time and will endure into an uncertain future, until they achieve grand unification. Among all the unknowns that irk them, modern cosmologists feel most acutely the lack of a theory that triumphantly blends quantum mechanics with general relativity. Meanwhile, these seemingly immiscible branches of physics, the science of the small and the science of the large, care not a whit for our ignorance. Instead, they coexist with remarkable success inside the same universe, mocking our attempts to understand them as a coherent whole. A galaxy with 100 billion stars apparently pays no particular attention to the physics of the atoms and molecules that compose its star systems and gas clouds. Neither do the even larger agglomerations of matter we call galaxy clusters and superclusters, themselves containing hundreds, sometimes thousands of galaxies. But these largest structures in the universe nonetheless owe their very existence to immeasurably small quantum fluctuations within the primeval cosmos. To understand how these structures arose, we must do the best we can in our current state of ignorance, passing from the minuscule domains governed by quantum mechanics, which hold the key to the origin of structure, to those so large that quantum mechanics plays no role. And matter obeys the laws laid down by general relativity. To this end, we must seek to explain the structure-laden universe that we see today as arising from a nearly featureless cosmos soon after the Big Bang. Any attempt to explain the origin of structure must also account for the cosmos in its present state. Even this modest task has confounded astronomers and cosmologists with a series of false starts and errors, from which we have now, so we may fervently hope, removed ourselves to walk in the bright light of a correct description of the universe. Throughout most of modern cosmology's history, astrophysicists have assumed that the distribution of matter in the universe can be described as both homogeneous and isotropic. In a homogeneous universe, every location looks similar to every other location, like the contents of a glass of homogenized milk. An isotropic universe is one that looks the same in every direction from any given point in space and time. These two descriptions may seem the same, but they are not. For example, the lines of longitude on Earth are not homogeneous, because they are farther apart in some regions and closer together in others. They are isotropic in just two places, the North and South Poles, where all lines of longitude converge. If you stand at either the top or bottom of the world, the longitude grid will look the same to you, no matter how far to the left or the right you turn your head. In a more physical example, imagine yourself atop a perfect, cone-shaped mountain, and imagine that this mountain is the only thing in the world. Then every view of Earth's surface from that perch would look the same. The same would be true if you happened to live in the center of an archery target, or if you were a spider at the center of its perfectly spun web. In each of these cases, your view will be isotropic, but decidedly not homogeneous. An example of a homogeneous but non-isotropic pattern appears in a wall of identical rectangular bricks, laid in a bricklayer's traditional, overlapping manner. On the scale of several adjoining bricks and their mortar, the wall will be the same everywhere, bricks, but different lines of sight along the wall will intersect the mortar differently, destroying any claim to isotropy. Intriguingly, mathematical analysis tells us that space will turn out to be homogeneous only if it is everywhere isotropic. Another formal theorem of mathematics tells us that if space is isotropic in just 3 places, then space must be isotropic everywhere. Yet some of us shun mathematics as uninteresting and unproductive. Although cosmologists were aesthetically motivated for assuming the homogeneity and isotropy of the distribution of matter in space, they have come to believe in this assumption enough to establish it as a fundamental cosmological principle. We might also call this the principle of mediocrity. Why should one part of the universe be any more interesting than another? On the smallest scales of size and distance, we easily recognize this assertion to be false. We live on a solid planet with an average density of matter close to 5.5 grams per cubic centimeter. Our Sun, a typical star, has an average density of about 1.4 grams per cubic centimeter. The interplanetary spaces between the two, however, have a significantly smaller average density, smaller by a factor of about 1 billion trillion. Intergalactic space, which accounts for most of the volume of the universe, contains less than 1 atom in every 10 cubic meters. Here the average density falls below the density of interplanetary space by another factor of 1 billion, enough to make the mind feel good about the occasional accusation of being dense. As astrophysicists expanded their horizons, they saw clearly that a galaxy such as our Milky Way consists of stars that float through nearly empty interstellar space. The galaxies likewise group into clusters that violate the assumption of homogeneity and isotropy. The hope remained, however, that as astrophysicists charted visible matter on the largest scales, they would find that galaxy clusters have a homogeneous and isotropic distribution. For homogeneity and isotropy to exist within a particular region of space, it must be large enough that no structures sit uniquely within it. If you take a melon ball sample of such a region, the requirements of homogeneity and isotropy imply that the region's overall properties must be similar in every way to the average properties of any other scoop with the same size. What an embarrassment it would be if the left half of the universe looked different from its right half. How large a region must we examine to find a homogeneous and isotropic universe? Our planet Earth has a diameter of 0.04 light seconds. Neptune's orbit spans 8 light hours. The stars of the Milky Way galaxy delineate a broad, flat disk about 100,000 light-years across. And the Virgo supercluster of galaxies, to which the Milky Way belongs, extends some 60 million light-years. So the coveted volume that can give us homogeneity and isotropy must be larger than the Virgo supercluster. When astrophysicists made surveys of the galaxy's distribution in space, they discovered that even on these scales of size, as large as 100 million light-years, the cosmos reveals enormous, comparatively empty gaps. Bounded by galaxies that have arranged themselves into intersecting sheets and filaments. Far from resembling a teeming, homogeneous anthill, the distribution of galaxies on this scale resembles a loofah sponge. Finally, however, astrophysicists made still larger maps, and found their treasured homogeneity and isotropy. Turns out, the contents of a 300 million light-year scoop of the universe does indeed resemble other scoops of the same size, fulfilling the long-sought aesthetic criterion for the cosmos. But, of course, on smaller scales, everything has clumped itself into distinctly non-homogeneous and non-isotropic distributions of matter. 3 centuries ago, Isaac Newton considered the question of how matter acquired structure. His creative mind easily embraced the concept of an isotropic and homogeneous universe, but promptly raised an issue that would not occur to most of us. How can you make any structure at all in the universe without having all the matter of the universe joining it to create one gigantic mass? Newton argued that since we observe no such mass, the universe must be infinite. In 1692, writing to Richard Bentley, the master of Trinity College at Cambridge University, Newton proposed that if all the matter in the universe were evenly scattered throughout all the heavens, and every particle had an innate gravity toward all the rest, and the whole space throughout which this matter was scattered was but finite, the matter on the outside of the space would, by its gravity, tend toward all the matter on the inside, and by consequence, fall down into the middle of the whole space and there compose one great spherical mass. But if the matter was evenly disposed throughout an infinite space, it could never convene into one mass, but some of it would convene into one mass and some into another, so as to make an infinite number of great masses, scattered at great distances from one to another throughout all that infinite space. Newton presumed that his infinite universe must be static, neither expanding nor contracting. Within this universe, objects were convened by gravitational forces, the attraction that every object with mass exerts on all other objects. His conclusion about gravity's central role in creating structure remains valid today, even though cosmologists face a task more daunting than Newton's. Far from enjoying the benefits of a static universe, we must allow for the fact that the universe has been expanding ever since the Big Bang, naturally opposing any tendency for matter to clump together by gravity. The problem of overcoming the cosmic expansion's anti-convening tendency becomes more serious when we consider that the cosmos expanded most rapidly soon after the Big Bang, the era when structures first began to form. At first glance, we could no more rely on gravity to form massive objects out of diffuse gas than we could use a shovel to move fleas across a barnyard. Yet somehow gravity has done the trick. During the early days of the universe, the cosmos expanded so rapidly that if the universe had been strictly homogeneous and isotropic on all size scales, gravity would have had no chance of victory. Today these would be no galaxies, stars, planets, or people, only a scattered distribution of atoms everywhere in space, a dull and boring cosmos, devoid of admirers and objects of admiration. But ours is a fun and exciting universe only because inhomogeneities and anisotropies appeared during those earliest cosmic moments, which served as a kind of cosmic soup starter for all concentrations of matter and energy that would later emerge. Without this head start, the rapidly expanding universe would have prevented gravity from ever gathering matter to build the familiar structures we take for granted in the universe today. What made these deviations, the inhomogeneities and anisotropies that provide the seeds for all the structure in the cosmos? The answer arrives from the realm of quantum mechanics, undreamt of by Isaac Newton but unavoidable if we hope to understand where we came from. Quantum mechanics tells us that on the smallest scales of size, no distribution of matter can remain homogeneous and isotropic. Instead, random fluctuations in the distribution of matter will appear, disappear, and reappear in different amount, as matter becomes a quivering mass of vanishing and reborn particles. At any particular time, some regions of space will have slightly more particles, and therefore a slightly greater density, than other regions. From this counterintuitive, airy-fairy fantasy, we derive everything that exists. The slightly denser regions had the chance to attract slightly more particles by gravity, and with time the cosmos grew these denser regions into structures. In tracing the growth of structure from times soon after the Big Bang, we can gain some insight from two key epochs we have already met, the era of inflation, when the universe expanded at an astounding rate, and the time of decoupling, about 380,000 years after the Big Bang, when the cosmic background radiation ceased to interact with matter. The inflationary era lasted from about 10 to 37 second to 10 to 33 second after the Big Bang. During that relatively brief stretch of time, the fabric of space and time expanded faster than light, growing in a billionth of a trillionth of a trillionth of a second from 100 billion times smaller than the size of a proton to about 4 inches. Yes, the observable universe once fit within a grapefruit. But what caused the cosmic inflation? Cosmologists have named the culprit, a phase transition that left behind a specific and observable signature in the cosmic background radiation. Phase transitions are hardly unique to cosmology, they often occur in the privacy of your home. We freeze water to make ice cubes, and boil water to produce steam. Sugary water grows sugar crystals on a string dangling within the liquid. And wet, gooey batter turns into cake when baked. There's a pattern here. In every case, things look very different on the two sides of a phase transition. The inflationary model of the universe asserts that when the universe was young, the prevailing energy field went through a phase transition, one of several that would have occurred during these early times. This particular episode not only catapulted the early, rapid expansion but also imbued the cosmos with a specific fluctuating pattern of high and low density regions. These fluctuations then froze into the expanding fabric of space, creating a kind of blueprint for where galaxies would ultimately form. Thus, in the spirit of Pooh Bah, the character in Gilbert and Sullivan's Mikado who proudly traced his ancestry back to a primordial atomic globule, we can assign our origins, and the beginnings of all structure, to the fluctuations on a subnuclear scale that arose during the inflationary era. What facts can we cite to support this bold assertion? Since astrophysicists have no way to see back to the universe's first zero. 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 and use scientific logic to connect this early epoch to times they can observe. If the inflationary theory is correct, the initial fluctuations produced during that era. The inevitable result of quantum mechanics, which tells us that small variations from place to place will always arise within an otherwise homogeneous and isotropic fluid, would have had the opportunity to become regions of high and low concentrations of matter and energy. We can hope to find evidence for these variations from place to place in the cosmic background radiation, which serves as a proscenium that separates the current epoch from, and also connects it with, the first moments of the neonate universe. As we have already seen, the cosmic background radiation consists of the photons generated during the first minutes after the Big Bang. Early in the universe's history, these photons interacted with matter, slamming into any atoms that happened to form so energetically that no atoms could exist for long. But the ongoing expansion of the universe in effect robbed the photons of energy, so that eventually, at the time of decoupling, none of the photons had energy sufficient to prevent electrons from orbiting around protons and helium nuclei. Since that time, 380,000 years after the Big Bang, atoms have persisted, unless some local disturbance, such as the radiation from a nearby star, disrupts them, while the photons, each with an ever-diminishing amount of energy, continue to roam the universe, collectively forming the cosmic background radiation or CBR. The CBR thus carries the imprint of history, a snapshot of what the universe was like at the time of decoupling. Astrophysicists have learned how to examine this snapshot with ever-increasing accuracy. First, the simple fact that the CBR exists, that their basic understanding of the history of the universe is correct. And then, after years of improving their abilities to measure the cosmic background radiation, their sophisticated balloon-borne and satellite instruments gave them a map of the CBR's tiny deviations from homogeneity. This map provides the record of the once minuscule fluctuations whose size increased as the universe expanded during the few 100,000 years after the era of inflation, and which then grew, during the next billion years or so, into the large-scale distribution of matter in the cosmos. Remarkable though it may seem, the CBR provides us with the means for mapping the imprint of the long-vanished early universe, and for locating, 14 billion light-years away in all directions, the regions of slightly greater density that would become galaxy clusters and superclusters. Regions with greater than average density left behind slightly more photons than regions with lower densities. As the cosmos became transparent, thanks to the loss of energy that left the photons unable to interact with the newly formed atoms, each photon embarked on a journey that would carry it far from its point of origin. Photons from our vicinity have traveled 14 billion light-years in all directions, providing part of the CBR that far-distant civilizations at the end of the visible universe may even now be examining, and their photons, having reached our instruments, tell us about what things. Through more than a quarter of a century following the first detection of the cosmic background radiation in 1965, astrophysicists searched for anisotropies in the CBR. From a theoretical viewpoint, they desperately needed to find them, because without the existence of CBR anisotropies at the level of a few parts in 100,000, their basic model of how structure appeared would lose all claim to validity. Without the seeds of matter they betray, we would have no explanation for why we exist. As happy fate would have it, the anisotropies appeared precisely on schedule. Just as soon as cosmologists created instruments capable of detecting anisotropies at the appropriate level, they found them, first with the COBE satellite in 1992, and later with far more precise instruments mounted on balloons and on the WMAP satellite described in Chapter 3. The teeny fluctuations from place to place in the amounts of microwave photons that form the CBR, now delineated with impressive precision by WMAP, embody the record of cosmic fluctuations at a time 380,000 years after the Big Bang. The typical fluctuation sits only a few 100,000ths of a degree above or below the average temperature of the cosmic background radiation, so detecting them is like finding faint spots of oil on a mile-wide pond that make the water plus oil a tiny bit denser than average. Small though these anisotropies were, they suffice to get things started. In the WMAP map of the cosmic background radiation, the larger hot spots tell us where gravity would overcome the expanding universe's dissipative tendencies and gather together enough matter to manufacture superclusters. These regions today have grown to contain about 1,000 galaxies, each with 100 billion stars. If we add the dark matter in such a supercluster, its total mass reaches the equivalent of 1,016 suns. Conversely, the larger cool spots, with no head start against the expanding universe, evolved to become nearly devoid of massive structures. Astrophysicists just call these regions voids, a term that gains meaning from being surrounded by something that is not a void. So the giant sheets and filaments of galaxies that we can trace on the sky not only form clusters at their intersections but also trace walls and other geometric forms that give shape to the empty regions of the cosmos. Of course, the galaxies themselves did not simply appear, fully formed, from concentrations of matter a tiny bit denser than average. From 380,000 years after the Big Bang until about 200 million years later, matter continued to gather itself together, but nothing shone in the universe, whose first stars were yet to be born. During this cosmic dark age, the universe contained only what it had made during its first few minutes, hydrogen and helium, with traces of lithium. With no elements heavier than these, no carbon, nitrogen, oxygen, sodium, calcium, or heavier elements, the cosmos contained none of the now common atoms or molecules that can absorb light as a star begins to shine. Today, in the presence of these atoms and molecules, the light from a newly formed star will exert pressure upon them that pushes away massive quantities of gas that would otherwise fall into the star. This expulsion limits the maximum mass of newborn stars to less than 100 times the Sun's mass. But when the first stars formed, in the absence of atoms and molecules that would absorb starlight, infalling gas consisted almost entirely of hydrogen and helium, providing only token resistance to stars' output. This allowed stars to form with much larger masses, up to many hundred, perhaps even a few thousand, times the mass of the Sun. Convert their matter into energy at astonishing rates, as they manufacture heavy elements and die explosive youthful deaths. Their life expectancies amount to no more than a few million years, less than 1,000th of the Sun's. We expect to find none of the most massive stars from that era alive today, because the early ones burnt themselves out long ago, and today, with heavier elements common throughout the universe, the highest mass stars of old cannot form at all. Indeed, none of the high-mass giants has ever been observed. But we assign them the responsibility for having first introduced into the universe almost all of the familiar elements we now take for granted, including carbon, oxygen, nitrogen, silicon, and iron. Call it enrichment. Call it pollution. But the seeds of life began with the long-vanished first generation of high-mass stars. During the first few billion years after the time of decoupling, gravitationally induced collapse proceeded with abandon, as gravity drew matter together on nearly all scales. One of the natural results of gravity at work was the formation of supermassive black holes, each with a mass millions or billions of times the mass of the Sun. Black holes with that amount of mass are about the size of Neptune's orbit and wreak havoc on their nascent environment. Gas clouds drawn toward these black holes want to gain speed, but they can't, because there's too much stuff in the way. Instead, they slam into and rub against whatever came in just before them, descending toward their master in a swirling maelstrom. Just before these clouds disappear forever, collisions within their superheated matter radiate titanic quantities of energy, billions of times the Sun's luminosity, all within the volume of a solar system. Monstrous jets of matter and radiation spew forth, extending hundreds of thousands of light-years above and below the swirling gas, as the energy punches through and escapes the funnel in all ways it can. As one cloud falls, and another orbits in waiting, the luminosity of the system fluctuates, getting brighter and dimmer over a matter of hours, days, or weeks. If the jets happen to be aimed straight at you, the system will look even more luminous, and more variable in its output, than those cases in which the jets point to the side. Viewed from any appreciable distance, all of these black hole, plus, infalling, matter combinations will appear amazingly small and luminous in comparison to the galaxies we see today. What the universe has created, the objects whose birth we have just witnessed in words, are quasars. Quasars were discovered during the early 1960s, as astronomers began to use telescopes equipped with detectors sensitive to invisible domains of radiation, such as radio waves and X-rays. Their galaxy portraits could therefore include information about the galaxy's appearance in those other bands of the electromagnetic spectrum. Combine this with further improvements in photographic emulsions, and a new zoo of galaxy species emerged from the depths of space. Most remarkable among them were objects that, in photographs, look like simple stars, but, quite unlike stars, produce extraordinary amounts of radio waves. The working description for those objects was quasi-stellar radio source, a term quickly shortened to quasar. Even more remarkable than the radio emission from these objects were their distances. As a class, they turned out to be the most distant objects known in the universe. For quasars to be that small and still visible at immense distances meant that they had to be an entirely new kind of object. How small? No bigger than a solar system. How luminous? Even the dim ones outshine your average galaxy in the universe. Engine, gravitationally devouring everything in its grasp. The black hole model can account for how small and bright quasars are, but says nothing of the black hole's source of food. Not until the 1980s would astrophysicists begin to understand the quasar's environment, because the tremendous luminosity of a quasar's central regions prevents any sight of its much fainter surroundings. Eventually, however, with new techniques to mask the light from the center, astrophysicists could detect fuzz surrounding some of the dimmer quasars. As detection tactics and technologies improved further, every quasar revealed fuzz, some even revealed a spiral structure. Quasars, it turned out, are not a new kind of object but rather a new kind of galactic nucleus. In April 1991, the National Aeronautics and Space Administration launched one of the most expensive astronomical instruments ever built, the Hubble Space Telescope. The size of a Greyhound bus, directed by commands sent from Earth, the Hubble telescope could profit from orbiting outside our ever-blurring atmosphere. Once astronauts had installed lenses to correct for mistakes in the way its primary mirror had been made, the telescope could peer into previously uncharted regions of ordinary galaxies, including their centers. Upon gazing into those centers, it found the stars moving inexcusably fast, given the gravity inferred from the visible light of other stars in the vicinity. Strong gravity, small area. Must be a black hole. Galaxy after galaxy, dozens of them, had suspiciously speedy stars in their cores. Indeed, whenever the Hubble Space Telescope had a clear view of a galaxy's center, they were there. It now seems likely that every giant galaxy harbors a supermassive black hole, which could have served as a gravitational seed around which the other matter collected or may have been manufactured later by matter streaming down from outer regions of the galaxy. But not all galaxies were quasars in their youth. The growing roster of ordinary galaxies known to have a black hole at their center began to raise eyebrows among investigators. A supermassive black hole that was not a quasar? A quasar that's surrounded by a galaxy? One can't help but think of a new picture of how things work. In this picture, some galaxies begin their lives as quasars. To be a quasar, which is really just the blazing visible core of an otherwise run-of-the-mill galaxy, the system has to have not only a massive, hungry black hole but also an ample supply of infalling gas. Once the supermassive black hole has gulped down all the available food, leaving uneaten stars and gas in distant, safe orbits, the quasar simply shuts off. You've then got a docile galaxy with a dormant black hole snoozing at its center. Astronomers have found other new types of objects, classified as intermediate between quasars and normal galaxies, whose properties also depend on the bad behavior of supermassive black holes. Sometimes the streams of material falling into a galaxy's central black hole flow slowly and steadily. At other times episodically. Such systems populate the menagerie of galaxies whose nuclei are active but not ferocious. Over the years, names for the various types accumulated: liners, Seyfert galaxies, N galaxies, blazars. All of these objects are generically called AGNs, the astrophysicists' abbreviation for galaxies with active nuclei. Unlike quasars, which appear only at immense distances, AGNs appear both at large distances and relatively nearby. This suggests that AGNs fill in the range of galaxies that misbehave. Quasars long ago consumed all their food, so we see them only when we look far back in time by observing far out in space. AGNs, in contrast, had more modest appetites, so some of them still have food to eat even after billions of years. Classifying AGNs solely on the basis of their visual appearance alone would provide an incomplete story, so astrophysicists classified AGNs by their spectra and by the full range of their electromagnetic emissions. During the mid to late 1990s, investigators improved their black hole model, and found that they could characterize nearly all the beasts in the AGN zoo by measuring only a few parameters: the mass of the object's black hole, the rate at which it's being fed, and our angle of view on the accretion disk and its jets. If, for example, we happen to look right down the barrel, along exactly the same direction as that of a jet emerging from the vicinity of a supermassive black hole, we see a much brighter object than if we happen to have a side view from a much different angle. Variations in these three parameters can account for nearly all the impressive diversity that astrophysicists observe, giving them a welcome despeciation of galaxy types and a deeper understanding of the formation and evolution of galaxies. The fact that so much can be accounted for. Differences in shape, size, luminosity, and color, by so few variables represents an unheralded triumph of late 20th century astrophysics. Because it took a lot of investigators and a lot of years and a lot of telescope time, it's not the sort of thing that gets announced on the evening news, but it's a triumph nonetheless. Let us not conclude, however, that supermassive black holes can explain everything. Even though they have millions or billions of times the Sun's mass, they contribute almost nothing in comparison with the masses of the galaxies in which they are embedded, typically far less than 1% of a large galaxy's total mass. When we seek to account for the existence of dark matter, or of other unseen sources of gravity in the universe, these black holes are insignificant and may be ignored. But when we calculate how much energy they wield, that is, when we compute the energy that they released as part of their formation, we find that black holes dominate the energetics of galaxy formation. All the energy of all the orbits of all the stars and gas clouds that ultimately compose a galaxy pales when compared with what made the black hole. Without supermassive black holes lurking below, galaxies as we know them might have never formed. The once luminous but now invisible black hole that lies at the center of each giant galaxy provides a hidden link, the physical explanation for the agglomeration of matter into a complex system of billions of stars in orbit around a common center. The broader explanation for the formation of galaxies invokes not only the gravity produced by supermassive black holes but also gravity in more conventional astronomical settings. What made the billions of stars in a galaxy? Gravity did this too, producing up to hundreds of thousands of stars in a single cloud. Most of a galaxy's stars were born within relatively loose associations. The more compact regions of starbirth remain identifiable, star clusters, within which member stars orbit the cluster's center, tracing their paths through space in a cosmic ballet choreographed by the forces of gravity from all the other stars within the cluster. Even as the clusters themselves move on enormous trajectories around the galactic center, safe from the destructive power of the central black hole. Within a cluster, stars move at a broad range of speeds, some so rapidly that they risk escape from the system altogether. This indeed occasionally occurs, as fast stars evaporate from the grip of a cluster's gravity to roam freely through the galaxy. These free-ranging stars, along with the globular star clusters, that contain hundreds of thousands of stars each, add to the stars that form the spherical halos of galaxies. Initially luminous, but today devoid of their brightest, short-lived stars, galaxy halos are the oldest visible objects in the universe, with birth certificates traceable to the formation of galaxies themselves. Last to collapse, and thus the last to turn into stars, we encounter the gas and dust that finds itself pulled and pinned into the galactic plane. In elliptical galaxies, no such plane exists, and all of their gas has already turned into stars. Spiral galaxies, however, have highly flattened distributions of matter, characterized by a central plane within which the youngest, brightest stars form in spiral patterns, testimony to great vibrating waves of alternating dense and rarefied gas that orbit the galactic center. Like hot marshmallows that stick together upon contact, all of the gas in a spiral galaxy that did not swiftly participate in making star clusters has fallen toward the galactic plane, stuck to itself, and created a disk of matter that slowly manufactures stars. For past billions of years, and for billions of years to come, stars will continue to form in spiral galaxies, with each generation more enriched in heavy elements than the next. These heavy elements have been cast forth into interstellar space by outflows from aging stars or as the explosive remains of high-mass stars, a species of supernova. Their existence renders the galaxy, and thus the universe, ever more friendly to the chemistry of life as we know it. We have outlined the birth of a classical spiral galaxy, in an evolutionary sequence that has played out tens of billions of times, yielding galaxies in a host of different arrangements, in clusters of galaxies, in long strings and filaments of galaxies, and in sheets of galaxies. Because we look back in time as we look outward into space, we possess the ability to examine galaxies not only as they are now but also as they appeared billions of years ago, simply by looking up. The problem with turning this concept into observational reality resides in the fact that galaxies billions of light-years away appear to us as extremely small and dim objects, so even our best telescopes can barely resolve their outlines. Nevertheless, astrophysicists have made great progress in this effort during the past few years. The breakthrough came in 1995, when Robert Williams, then the director of the Space Telescope Science Institute at Johns Hopkins University, arranged for the Hubble telescope to point toward a single direction in space, near the Big Dipper, for 10 days' worth of observation. Williams deserves the credit because the telescope's time allocation committee, which selects the observing proposals most worthy of actual telescope time, judged it unworthy of support. After all, the region to be studied was deliberately chosen for having nothing interesting to look at, and thus to represent a dull and boring patch of sky. As a result, no ongoing projects could benefit directly from such a large commitment of the telescope's highly oversubscribed observing time. Happily, Williams, as the director of the Space Telescope Science Institute, had the right to assign a few percent of the total, his director's discretionary time, and invested his clout on what became known as the Hubble Deep Field, one of the most famous astronomical photographs ever taken. The 10-day exposure, coincidentally made during the government shutdown of 1995, produced by far the most researched image in the history of astronomy. Studded with galaxies and galaxy-like objects, the deep field offers us a cosmic palimpsest, in which objects at different distances from the Milky Way have written their momentary signatures of light at different times. We see objects in the deep field as they were, say, 1.3 billion, 3.6 billion, 5.7 billion, or 8.2 billion years ago, with each object's epoch determined by its distance from us. Hundreds of astronomers have seized upon the wealth of data contained in this single image to derive new information about how galaxies have evolved with time, and about how galaxies looked soon after they formed. In 1998, the telescope secured a companion image, the Hubble Deep Field South, by devoting 10 days of observation to another patch of sky in the direction opposite to that of the first deep field, in the celestial southern hemisphere. Comparison of the two images allowed astronomers to assure themselves that the results from the first deep field did not represent an anomaly, and to refine their conclusions about how different types of galaxies form. After a successful servicing mission, in which the Hubble telescope was outfitted with even better detectors, the Space Telescope Science Institute just couldn't resist and, in 2004, authorized the Hubble Ultra Deep Field, laying bare the ever more distant cosmos. Unfortunately, the earliest stages of galaxy formation, which would be revealed to us by objects at the greatest distances, confound even the Hubble telescope's best efforts, not least because the cosmic expansion has shifted most of their radiation into the infrared region of the spectrum, not accessible to the telescope's instruments. For these most distant galaxies, astronomers await the design, construction, launch, and successful operation of the Hubble successor, the James Webb Space Telescope, named after the head of NASA during the Apollo era. The JWST will have a mirror larger than Hubble's, designed to unfurl itself like an intricate mechanical flower, opening in space to provide a reflective surface much larger than any that can fit inside one of our rockets. The new space telescope will also possess a suite of instruments far superior to those of the Hubble telescope, which were originally designed during the 1960s, built during the 1970s, launched in 1991. And, even though significantly upgraded during the 1990s, still lack such fundamental abilities as the capacity to detect infrared radiation. Some of this ability now exists in the Spitzer Infrared Telescope facility, launched in 2003, which orbits the Sun much farther from Earth than the Hubble does, thereby avoiding interference from the copious amounts of infrared radiation produced by our planet. To achieve this goal, JWST will likewise have an orbit much farther from Earth than the Hubble telescope does, and will therefore be forever inaccessible to servicing missions as they are currently conceived. NASA had better get this one right the first time. If the new telescope goes into operation in 2011, as currently planned, it should then provide spectacular new views of the cosmos, including images of galaxies more than 10 billion light-years away, seen much closer to their time of origin than any revealed by the Hubble deep fields. Working in tandem with the new space telescope, as they have with the old, large ground-based instruments will study in detail the wealth of objects to be revealed by our next great step in spaceborne instrumentation. Rich in possibility though the future may be, we should not neglect the astrophysicists' impressive accomplishments during the past 3 decades, which spring from their abilities to create new instruments to observe the universe. Carl Sagan liked to say that you had to be made from wood not to stand in awe of what the cosmos has done. Thanks to our improved observations, we now know more than Sagan did about the amazing sequence of events that led to our existence, the quantum fluctuations in the distribution of matter and energy on a scale smaller than the size of a proton that spawns superclusters of galaxies 30 million light-years across. From chaos to cosmos, this cause and effect relationship crosses more than 38 powers of 10 in size and 42 powers of 10 in time. Like the microscopic strands of DNA that predetermine the identity of a macroscopic species and the unique properties of its members, the modern look and feel of the cosmos was writ in the fabric of its earliest moments, and carried relentlessly through time and space. We feel it when we look up. We feel it when we look down. We feel it when we look within. The origin of stars. Chapter 9. Dust to dust. If you look at the clear night sky far from city lights, you can immediately locate a cloudy band of pale light, broken in places by dark splotches, that runs from horizon to horizon. Long known as the Milky Way, in the sky, this milk-white haze combines the light from a staggering number of stars and gaseous nebulae. Those who observe the Milky Way with binoculars or a backyard telescope will see the dark and boring areas resolve themselves into, well, dark and boring areas, but the bright areas will turn from a diffuse glow into countless stars and nebulae. In his small book Sidereus Nuncius, published in Venice in 1610, Galileo Galilei provided the first account of the heavens as seen through a telescope, including a description of the Milky Way's patches of light. Referring to his instrument as a spyglass, since the name telescope had yet to be coined, Galileo could barely contain himself. The Milky Way itself, which, with the aid of the spyglass, may be observed so well that all the disputes that for so many generations have vexed philosophers are destroyed by visible certainty, and we are liberated from wordy arguments. For the galaxy is nothing else than a congeries of innumerable stars distributed in clusters. To whatever region of it you direct your spyglass, an immense number of stars immediately offer themselves to view, of which very many appear rather large and very conspicuous, but the multitude of small ones is truly unfathomable. Surely Galileo's immense number of stars, which delineate the most densely packed regions of our Milky Way galaxy, must locate the real astronomical action. Why, then, should anybody be interested in the intervening dark areas with no visible stars? Based on their visual appearance, the dark areas are probably cosmic holes, openings to the infinite and empty spaces beyond. 3 centuries would pass before anyone figured out that the dark patches in the Milky Way, far from being holes, actually consist of dense clouds of gas and dust that obscure more distant star fields and hold stellar nurseries deep within themselves. Following earlier suggestions by the American astronomer George Carey Comstock, who wondered why faraway stars are much dimmer than their distances alone would indicate, the Dutch astronomer Jacobus Cornelius Kapteyn in 1909 identified the culprit. In two research papers, both titled On the Absorption of Light in Space, Kapteyn presented evidence that the dark clouds, his newfound interstellar medium, not only block the light from stars but also do so unevenly across the rainbow of colors in a star's spectrum. They absorb and scatter, and therefore attenuate, light at the violet end of the visible spectrum more effectively than they act on red light. This selective absorption preferentially removes more violet than red light, making faraway stars appear redder than nearby ones. The amount of this interstellar reddening of starlight increases in proportion to the total amount of material that the light encounters on its journey to us. Ordinary hydrogen and helium, the principal constituents of cosmic gas clouds, don't redden light. But molecules made of many atoms do so, especially those that contain the elements carbon and silicon. When interstellar particles grow too large to be called molecules, with hundreds of thousands or millions of individual atoms in each of them, we call them dust. Most of us know dust of the household variety, although few of us care to learn that, in a closed home, dust consists mostly of dead, sloughed-off human skin cells. As far as we know, cosmic dust contains nobody's epidermis. However, interstellar dust does include a remarkable ensemble of complex molecules, which emit photons primarily in the infrared and microwave regions of the spectrum. Astrophysicists lacked good microwave telescopes until the 1960s, and effective infrared telescopes until the 1970s. Once they had created these observational instruments, they could investigate the true chemical richness of the stuff that lies between the stars. During the decades that followed these technological advances, a fascinating, intricate picture of star birth emerged. Not all gas clouds will form stars at all times. More often than not, a cloud finds itself confused about what to do next. Actually, astrophysicists are the confused ones here. We know that an interstellar cloud wants to collapse under its own gravity to make one or more stars. But the cloud's rotation, as well as the effects of turbulent gas motions within the cloud, oppose that result. So, too, does the gas pressure that you learned about in high school chemistry class. Magnetic fields can also fight collapse. They penetrate the cloud and constrain the motions of any free-roaming charged particles contained therein, resisting compression and thus impeding the ways in which the cloud can respond to its own gravity. The scary part of this thought exercise comes from the realization that if no one knew in advance that stars exist, frontline research would offer plenty of convincing reasons why stars could never form. Like the several hundred billion stars in our Milky Way galaxy, named after the band of light that the galaxy's most densely populated regions paint across our skies, giant clouds of gas orbit our galaxy's center. The stars amount to tiny specks, only a few light seconds across, that float in a vast ocean of nearly empty space, occasionally passing close by one another like ships in the night. Gas clouds, on the other hand, are huge. Typically spanning hundreds of light years, they each contain as much mass as 1,000,000 suns. As these giant clouds lumber through the galaxy, they often collide with one another, entangling their gas and dust-laden innards. Sometimes, depending on their relative speeds and their angles of impact, the clouds stick together. At other times, adding injury to the insult of collision, they rip each other apart. If a cloud cools to a sufficiently low temperature, its constituent atoms will stick together when they collide, rather than careening off one another as they do at higher temperatures. This chemical transition has consequences for everybody. The growing particles, now containing tens of atoms each, begin to scatter visible light to and fro, strongly attenuating the light of the stars behind the cloud. By the time that the particles become full-grown dust grains, they each contain billions of atoms. Aging stars manufacture similar dust grains and blow them gently into interstellar space during their red giant phases. Unlike smaller particles, dust grains with billions of atoms no longer scatter the visible light photons from the stars behind them. Instead, they absorb those photons and then re-radiate their energy as infrared, which can easily escape from the cloud. As this occurs, the pressure from the photons, transmitted to the molecules that absorb it, pushes the cloud in the direction opposite to the direction of the light source. The cloud has now coupled itself to starlight. Star birth occurs when the forces that make a cloud progressively denser eventually lead to its gravitationally induced collapse, during which each part of the cloud pulls all the other parts much closer. Since hot gas resists compression and collapse more effectively than cool gas does, we face an odd situation. We must cool the cloud before it can ever heat itself by producing a star. In other words, the creation of a star that possesses a 10 million degree core, sufficiently hot for thermonuclear fusion to begin, requires that the cloud must first achieve its coldest possible internal conditions. Only at extremely cold temperatures, a few dozen degrees above absolute zero, can the cloud collapse and allow star formation to begin in earnest. What happens within a cloud to turn its collapse into newborn stars? Astrophysicists can only gesticulate. Much as they would like to track the internal dynamics of a large, massive interstellar cloud, the creation of a computer model that includes the laws of physics, all the internal and external influences on the cloud, and all the relevant chemical reactions that can occur within it still lies beyond our abilities. A further challenge resides in the humbling fact that the original cloud has a size billions of times larger than that of the star we are trying to create, which in turn has a density 100 sextillion times the average density within in the cloud. In these situations, what matters most on one scale of sizes may not be the right thing to worry about on another. Nevertheless, relying on what we see throughout the cosmos, we can safely assert that within the deepest, darkest, densest regions of an interstellar cloud, where temperatures fall to about 10 degrees above absolute zero, gravity does cause pockets of gas to collapse, easily overcoming the resistance offered by magnetic fields and other impediments. The contraction converts the cloud pocket's gravitational energy into heat. The temperature within each of these regions, soon to become the core of a newborn star, rises rapidly during the collapse, breaking apart all the dust grains in the immediate vicinity as they collide. Eventually, the temperature in the central region of the collapsing gas pocket reaches the crucial value of 10 million degrees on the absolute scale. At this magic temperature, some of the protons move fast enough to overcome their mutual repulsion. Their high speeds allow the protons to approach one another closely enough for the strong nuclear force to make them bond. This force, which operates only at extremely short distances, binds together the protons and neutrons in all nuclei. The thermonuclear fusion of protons, thermo, because it occurs at high temperatures, and nuclear fusion, because it fuses particles into a single nucleus, creates helium nuclei, each of which has a mass slightly less than the sum of the particles from which it fused. The mass that disappears during this fusion turns into energy, in a balance described by Einstein's famous equation. The energy embodied in mass can be converted into other forms of energy, such as additional kinetic energy, of the fast-moving particles that emerge from nuclear fusion reactions. As the new energy produced by nuclear fusion diffuses outward, the gas heats and glows. Then, at the star's surface, the energy formerly locked in individual nuclei escapes into space in the form of photons, generated by the gas as the energy released through fusion heats it to thousands of degrees. Even though this region of hot gas still resides within the cosmic womb of a giant interstellar cloud, we may nonetheless announce to the Milky Way that a star is born. Astronomers know that stars range in mass from a mere 1/10 of the Sun's to nearly 100 times our star's mass. For reasons not well understood, a typical giant gas cloud can develop a multitude of cold pockets that all tend to collapse at about the same time to give birth to stars, some puny and others giants. But the odds favor the puny. For every high-mass star, 1,000 low-mass stars are born. The fact that no more than a few % of all the gas in the original cloud participates in star birth presents a classic challenge in explaining star formation. What makes the star-forming tail wag the largely unchanged dog of an interstellar gas cloud? The answer probably lies in the radiation produced by newborn stars, which tends to inhibit further star formation. We can easily explain the lower bound on the masses of newborn stars. Pockets of collapsing gas with masses less than about 1/10 of the Sun's have too little gravitational energy to raise their core temperatures to the 10 million degrees required for the nuclear fusion of hydrogen. In that case, no nuclear fusing star will be born. Instead, we obtain a failed, would-be star, an object that astronomers call a brown dwarf. With no energy source of its own, a brown dwarf fades steadily, shining from the modest heat generated during the original collapse. The gaseous outer layers of a brown dwarf are so cool that many of the large molecules normally destroyed in the atmospheres of hotter stars remain alive and well within them. Their feeble luminosities make brown dwarfs immensely difficult to detect, so to find them, astrophysicists must employ complex methods similar to those they occasionally use to detect planets, searching for the faint infrared glow from these objects. Only in recent years have astronomers discovered brown dwarfs in numbers sufficient to classify them into more than one category. We can also easily determine the upper mass limit to star formation. A star with a mass greater than about 100 times the Sun's will have a luminosity so great, such an enormous outpouring of energy in the form of visible light, infrared, and ultraviolet, that any additional gas and dust attracted toward the star will be pushed away by the intense pressure of starlight. The star's photons push on the dust grains within the cloud, which in turn carry the gas away with them. Here starlight couples irreversibly to dust. This radiation pressure operates so effectively that just a few high-mass stars within a dark, obscuring cloud will have luminosity sufficient to disperse nearly all its interstellar matter, laying bare to the universe dozens, if not hundreds, of brand new stars, all siblings. Really, for the rest of the galaxy to see. Whenever you gaze at the Orion Nebula, located just below the three bright stars of Orion's belt, midway along the Hunter's somewhat fainter sword, you can see a stellar nursery of just this sort. Thousands of stars have been born within this nebula, while thousands more await their birth, soon to create a giant star cluster that becomes more and more visible to the cosmos as the nebula dissipates. The most massive new stars, forming a group called the Orion Trapezium, are busy blowing a giant hole in the middle of the cloud from which they formed. Hubble telescope images of this region reveal hundreds of new stars in this zone alone, each infant swaddled within a nascent protoplanetary disk made of dust and other molecules drawn from the original cloud. And within each of these disks, a planetary system is forming. 10 billion years after the Milky Way formed, star formation continues today at multiple locations in our galaxy. Even though most of the star formation that will ever occur in a typical giant galaxy like ours has already taken place, we are fortunate that new stars continue to form, and will do so for many billion years to come. Our good fortune lies in our ability to study the formation process and the youngest stars, seeking clues that will reveal, in all its glory, the complete story of how stars pass from cold gas and dust to luminous maturity. How old are the stars? No star wears its age on its sleeve, but some show their ages in their spectra. Among the various means that astrophysicists have devised to judge the ages of stars, spectra forms the most reliable hinge for analyzing the different colors of starlight in detail. Every color, every wavelength and frequency of the light waves we observe, tells a story about how matter made the starlight, or affected that light as it left the star, or happened to lie along the line of sight between ourselves and the star. Through close comparison with laboratory spectra, physicists have determined the multitude of ways that different types of atoms and molecules affect the rainbow of colors in visible light. They can apply this fertile knowledge to observations of stellar spectra, and deduce the numbers of atoms and molecules that have affected light from a particular star, as well as the temperature, pressure, and density of those particles. From years of comparing laboratory spectra with the spectra of stars, together with laboratory studies of the spectra of different atoms and molecules, astrophysicists have learned how to read an object's spectrum like a cosmic fingerprint. One that reveals what physical conditions exist within a star's outer layers, the region from which light streams directly outward into space. In addition, astrophysicists can determine how atoms and molecules floating in interstellar space at much cooler temperatures may have affected the spectrum of the starlight they observe, and can likewise deduce the chemical composition, temperature, density, and pressure of this interstellar matter. In this spectral analysis, each different type of atom or molecule has its own story to tell. The presence of molecules of any type, for example, revealed by their characteristic effects on certain colors in the spectrum, demonstrates that the temperature in a star's outer layers must be less than about 3,000 Celsius. At higher temperatures, molecules move so rapidly that their collisions break them apart into individual atoms. By extending this type of analysis over many different substances, astrophysicists can derive a nearly complete picture of the detailed conditions in stellar atmospheres. Some hard-working astrophysicists are said to know far more about the spectra of stars they love than they do about their own families. This may have its downside for interpersonal relations, even as it